start of class. We're going to start our lecture for today, continuing on with chapter 22. Last class session, we discussed methods for enolate alkylation, and we talked about the reactions of enols and enolates. So in that note, we're going to talk about a unique structural motif, such as the malonic ester and other beta ketoesters that are used in organic synthesis to allow regioselective and easily controlled polyalkylation reactions. So the malonic ester synthesis is incredibly useful to convert alkyl halides into highly substituted carboxylic acids. The malonic ester synthesis utilizes very similar enolate alkylation reactions. However, the main benefit of the malonic ester synthesis is that malonic esters, for example, such as diethyl propane dioate, have a pK of around 13 and are fairly acidic. Thus, you can readily convert this malonic ester into its corresponding enolate using relatively weak bases such as ethoxide. The other thing I'd like you to note, because the malonic ester is quite acidic and ethoxide is relatively basic in this context, we can generate this malonic ester enolate quite readily, and this enolate will be product favored. From here, we can alkylate our enolate with any common, generally primary alkyl halide, to prepare an alkylated malonic ester. So we're generating our enolate. Because malonic esters are more acidic, enolate generation occurs readily. And from there, we can alkylate our enolate with common primary and some secondary alkyl halides. Does this general scheme make sense to everyone? Does this general scheme for the malonic ester synthesis make sense? So we make our enolate and then we alkylate it. Okay. So from here, we can actually further alkylate this malonic ester. So we take our product from the first alkylation reaction, and if we treat it with a second equivalent of base, such as ethoxide, we can again generate another enolate. And it's quite easy to generate this enolate quantitatively. From here, we can alkylate our malonic ester enolate with a second, potentially different alkyl halide. This gives us a dialkylated malonic ester. So we can control the alkylation reactions and we can generate mixed alkylation products with chemoselectivity. Does this next part make sense? So how do we get the carboxylic acid? So let's just talk about the first two steps for the malonic ester synthesis. So we're generating an enolate and then alkylating your malonic ester enolate. So for example, if you start with diethyl propane dioate and you treat it with ethoxide, you'll first deprotonate your highly acidic alpha protons and generate your malonic ester enolate. From here, the enolate is a competent carbon-centered nucleophile that can react with common electrophile such as your alkyl halide. So we displace our halide via an SN2 reaction, and we get our alkylated malonic ester product. From here, we can isolate this monoalkylation product, or we can take this alkylation product and treat it with another equivalent of ethoxide, to generate a new enolate. From here, if we treat this enolate with a second, potentially different alkyl halide, we can generate our second alkylated malonic ester. As you notice, one benefit of the malonic ester synthesis is that we can get highly substituted malonic esters and carboxylic acid derivatives with this method. Does this mechanism make sense for the dialkylation of a malonic ester? The key thing to note, the alkyl halides can be different, and you can stop this reaction at any stage. So by controlling the equivalence of base and controlling the amounts of alkyl halide, you can directly control what alkyl group is installed and whether the alkyl groups are the same or different. Does this make sense to everyone? Any questions I can address on the mechanism for malonic ester alkylation? If we don't have any other questions, let's move on then. So in order to prepare your carboxylic acid or carboxylic acid derivative, we're going to need to hydrolyze and decarboxylate this malonic ester. So malonic esters are unique, similar to beta ketoesters, in that upon treatment with strong acid and heat, they decarboxylate to yield a carboxylic acid and carbon dioxide. So the carbon dioxide came from one of our malonic ester substituents. So to talk a little bit about this general reaction, which is the decarboxylation of beta ketoacids, the decarboxylation reaction is a concerted reaction that requires a carbonyl group 2 atoms away from your carboxylic acid. So you need to have a beta keto functionality. So in this case, it's a concerted reaction where we abstract a proton and we lose carbon dioxide to generate your carboxylic acid enol. From here, this carboxylic acid enol then tautomerizes under the reaction conditions to yield the corresponding carboxylic acid. Does this mechanism for the decarboxylation of a diacid make sense? Does this first decarboxylation make sense? It's a concerted reaction where we abstract a proton from our carboxylic acid, we form a carbon-oxygen double bond, and we break our carbon-carbon bond to lose carbon dioxide and generate your carboxylic acid enol. From there, the enol tautomerizes to the corresponding carboxylic acid keto form. Any questions before we move on? Okay, let's look at the same mechanism for decarboxylation, this time if we have a beta ketoacid. The fundamental mechanism is identical. We only need a carbonyl functionality, 2 carbons away from our carboxylic acid that we want to decarboxylate. And again, we abstract a hydrogen, we form a carbon-oxygen double bond, and we lose carbon dioxide to generate our enol tautomer. Now, the enol tautomer can be used for reactions with electrophiles, but in most cases under the reaction conditions, we just end up tautomerizing this enol to the corresponding keto form. So at the end of this decarboxylation, we can convert a diacid into a carboxylic acid or a beta ketoacid into a ketone. Does this make sense? Any questions on this mechanism? Okay. So let's just walk through the full mechanism for decarboxylation, starting from the alkylated malonic ester. So suppose we have an alkylated malonic ester, and we want to prepare the corresponding carboxylic acid. Well, first, we can hydrolyze this ester and decarboxylate in the same reaction pot. So for the first step, we're going to need to hydrolyze this ester under acidic conditions. So we're going to first protonate one of our ester carbonyls. That in turn activates the ester for attack with even weak nucleophiles such as water. So from here, water will attack the electrophilic carbonyl carbon, and that will give us a tetrahedral intermediate. From here, we're going to see a series of proton transfers. We're going to need to activate this ester alcohol as a leaving group. And to accomplish that, we are going to protonate our ester alcohol. And we're going to free up a lone pair on oxygen. From here, we've now set up and prepared our ester alcohol as a leaving group. So we can then kick out that leaving group. To regenerate our ester carbonyl. Okay, so we've hydrolyzed one of our esters, but we're not done because this hydrolysis reaction is going to keep going. Now, it's unclear mechanistically whether you would see decarboxylation before or after the second hydrolysis. We're just going to hydrolyze both of our esters. So again, we're hydrolyzing the second ester, so we have to protonate the second ester carbonyl. And again, we're going to repeat this general mechanism where we protonate our carbonyl, attack with water, and after a proton transfer, we lose the equivalent of ethanol. So water attacks, we make a tetrahedral intermediate. Again, to activate our leaving group, we're going to protonate our ester alcohol and free up a lone pair on our oxygen that came from water. Okay, so we're now approaching the key step for this reaction. We're just about to get our dicarboxylic acid, and we're now ready for probably the most important part of this malonic ester synthesis mechanism, which is our key decarboxylation step. Okay, so we've lost ethanol. We now have our dicarboxylic acid, and we have one more cleanup step that we have to do. I know this mechanism seems a little bit long, but it's mostly repetition. We've done 2 hydrolysis steps. We're cleaning this up and removing our proton. And now we have our dicarboxylic acid ready to go. And I really like when I'm drawing out this mechanism to draw out the carboxylic acid in a way that makes it easy for me to show this decarboxylation. So to do that, what I'm going to do is I'm going to position my carboxylic acid like so, just really showing that 6-membered transition state, because this is a concerted reaction. And now we're ready for the key step, where we abstract a hydrogen from one of our carboxylic acids. We form a carbon-oxygen double bond, and in turn, we generate the enol tautomer of our carboxylic acid. So this is our key step. I'll label it as such. And from here, we get the corresponding enol tautomer. But this doesn't stick around for very long, right? The enol tautomer is not particularly favored at equilibrium, and it readily tautomerizes to the corresponding carboxylic acid, or I like to think of it like the keto tautomer. And that in turn gives us our desired neutral isolable substituted carboxylic acid. So just to review this mechanism, I'll zoom out just so that way everyone can catch the full mechanism. It takes a little bit, but it's nothing that we can't handle. So let me just scroll down to the page. So just to give the highlights here, we hydrolyze both of our esters. From here, once we have our dicarboxylic acid, we have a 6-membered transition state. This is a concerted reaction where we lose an equivalent of carbon dioxide and we get out the enol tautomer. Under the reaction conditions, the enol tautomer tautomerizes to the carboxylic acid, quote unquote, keto form. Does this mechanism make sense to everyone? The hydrolysis mechanism we've seen before. In terms of what's new, this decarboxylation mechanism is the only really new step that we've seen. Any questions on this mechanism before we try to apply what we've learned? So,
can you
yes.
scroll up a little bit, please?
Sure.
Or sorry, down.
Sure.
One last question. Will we be going over the practice exam during the lab time as well?
On Wednesday, yes, but we will.
Oh, okay. So we're not taking the exam this Wednesday?
It'll be open on Thursday.
Okay, for our section as well?
Yes, that's correct.
Oh, okay. Gotcha. Thank you.
That's to answer the question in the chat, that's for the Tuesday, Thursday section. Just because the schedule for this week is the Monday, Wednesday sections, they lecture Monday and Wednesday. But the test taking period starts on Thursday. We can talk more about that during lab today. Any other questions on this mechanism before we move on?
So in that key step, there's like a bond breaking there?
Yes,
Like that.
yes, we're breaking this carbon-carbon bond in our decarboxylation step.
So that would just be like floating around then?
Yeah,
Or...
we lose carbon dioxide. So during this process, we lose an equivalent of carbon dioxide.
Okay.
Does that make sense?
Yeah.
Perfect. So in terms of the overall conversion in the malonic ester synthesis, it's used to convert an alkyl halide into a carboxylic acid. And interestingly enough, it can be used to prepare highly substituted carboxylic acid as well as beta ketoester derivatives. So it's quite a useful reaction. And one of the reasons why we go through the malonic ester is because these protons are relatively acidic. They're easy to deprotonate. It's easy to make a malonic ester enolate. And it allows us to more effectively control reactivity so that we see monoalkylation, and generally just in terms of planning, going through this malonic ester or another beta ketoester allows us to control where we generate our enolate, and then we can remove this group via decarboxylation. Okay, so let's try to apply what we've learned, and let's take a look at the following reaction. In this case, we're treating a malonic ester derivative with tert butoxide and chloroethane. In this case, we're asked to predict the product of the following reaction and then draw a mechanism for this reaction. So let's take about 3 to 4 minutes to work through this example, and I'd like students to share their proposed responses in terms of their predicted product and the mechanism for this reaction in the chat, verbally, or annotated directly onto the class whiteboard. So we're treating a malonic ester with tert butoxide and chloroethane, and I'll just note one equivalent of each. So 1 mole equivalent of each. So what happens in this reaction? What would we expect to see if we treat a malonic ester with base followed by an alkyl halide such as chloroethane? Would anyone like to try and share their proposed mechanism as either a photo in the chat or an annotation on the class whiteboard? Or are there any questions that I can address as we work through this example to help advance our discussion? So we have students sharing their thoughts. So we have one student mentioning, well, T-butoxide is a base and these malonic ester protons are acidic. So we can pull off these acidic alpha protons. So we have one student proposing this first deprotonation step where tert-butoxide pulls off the acidic alpha proton and we make a malonic ester enolate. Okay, so now that we have this enolate, what is going to happen when we treat this nucleophilic enolate with an electrophile such as chloroethane? Would anyone like to draw the mechanism for this second step? Or would anyone like to try and explain what's going to happen in this second step? So we've deprotonated our alpha position and we've made an enolate. And as we've learned last class session, enolates are nucleophilic and they can react with electrophiles. So in this case, our carbon-centered nucleophile, which is our enolate, will attack the electrophilic alkyl halide carbon and displace your halogen. Perfect. Would you be able to draw the structure of the product that you get from this alkylation step? Yep, exactly right. This alkylation installs our alkyl group at the alpha position. Perfect. So these student proposed mechanisms look great. So let me clear the annotations and let's move on and let's re-annotate the next step in this mechanism. So as the students have quite accurately noted, when we have this enolate, the enolate functions as a carbon-centered nucleophile, and it can attack electrophiles such as this alkyl halide via a textbook SN2 reaction. That gives us our alkylated malonic ester. Perfect. So this is a textbook enolate alkylation mechanism. And the reason why this alkylation stops at the first alkylation is because this malonic ester is so acidic, we can generate the enolate quantitatively and then add our alkyl halide. And that allows us to control our reactivity. Does this mechanism make sense to everyone? Okay, so let's look at the next part. So we talked about enolate alkylation reactions, and we showed that we can alkylate malonic esters and beta ketoesters. Now let's look at this next step where we have a beta ketoester and we treat it with strong acid and heat. The last example, this is the SN2 reaction right here, where our nucleophile attacks the electrophilic carbon and displaces the leaving group. No, it's more than okay to ask. Did that address your question? Perfect. Okay, so let's make sure we understand the second step of the malonic ester synthesis. Once we have this alkylated, in this case, beta ketoester, if we treat it with acid and heat, we have students already commenting in the chat, we're going to see decarboxylation, aren't we? Yes, this is a textbook decarboxylation reaction. We've alkylated our alpha position. We have a carbonyl functionality, 2 carbons away from our ester, which is a carboxylic acid precursor. If we treat this beta ketoester with strong acid and heat, we are going to see decarboxylation, but let's make sure that our steps in the mechanism are clear. In order to get decarboxylation, we have to first make the carboxylic acid, and then we decarboxylate. And then there's one other step after in order to get our desired isolable major product. So let's try to work through the mechanism for this reaction, and let's try to predict the product from this reaction. And I'd love for students to share their responses in the chat, verbally, or annotated onto the class whiteboard. And if there are any questions I can address as you work through this example, don't be shy to send your proposed responses in the chat, verbally, or annotate on the class whiteboard. And if there are any questions I can address, don't be shy to ask them in the chat or verbally. In this case, I would focus on the productive pathway. So you can protonate the ketone, but it doesn't get us anywhere at first. Since when we want to convert this ester to the carboxylic acid, we need to activate the ester carbonyl carbon. And the best way to do that is via protonation. So would anyone like to try to share their mechanism on the class whiteboard? Or would anyone like to try to describe the first few steps of this mechanism? There's plenty of space on the class whiteboard. So if anyone would like to start us off on this problem or share their thoughts, anything to help advance this discussion. We've seen examples of this hydrolysis decarboxylation mechanism before, and let's try to put what we've learned into practice in solving this example. Okay, so we have one student proposing that as we need to get a carboxylic acid, we're going to need to hydrolyze this ester. So as always, in any carbonyl substitution reaction, such as hydrolysis, the first thing that we need to do is activate the ester via protonation. The student then went on to comment in the chat that now that we've protonated our ester carbonyl oxygen, we can then attack our ester carbonyl carbon with a nucleophile such as water. Okay, so we now have this tetrahedral intermediate. Would anyone like to pick up from where we left off? So this is as far as I've transcribed. This is where students have gotten so far by sharing their responses in the chat and sharing some photos of their proposed mechanism in the chat. So would anyone like to continue on from here? We have a few students commenting now, okay, we need to kick out this equivalent of ethanol. So there's going to be a proton transfer. So we're going to free up a lone pair on this oxygen, and then we're going to protonate our alcohol. So far, so good. And now that we've completed this proton transfer, we're just about ready to kick out our wonderful protonated leaving group to generate our desired carboxylic acid. Okay, so now we have this tetrahedral intermediate. What happens next? So we're going to kick down and reform our carbonyl, and we're going to lose an equivalent of ethanol. Yep, perfectly reasonable. So from here, that gives us our carboxylic acid. Okay, so from here, we're now approaching the key step for this decarboxylation reaction. Would anyone like to share a photo of their work, or would anyone like to try and annotate these next few steps? Just because the exact arrow pushing for these next few steps is very important, and I want to make sure it's accurate. So would anyone like to try to pick up where we left off and try to continue on with this mechanism? Does anyone have any thoughts on this mechanism as we work through this example? So we have our protonated carboxylic acid right now. So what do we have to do as a cleanup step before decarboxylation? So first we're going to pull off this proton from this highly acidic protonated carboxylic acid. Perfect. Okay, so we now have our beta keto carboxylic acid. Okay. Now from here, would anyone like to try and show the key decarboxylation step? Would anyone like to try to show and share an arrow pushing mechanism for this decarboxylation step? So we're going to pull off a proton, form a carbon-oxygen double bond, and then lose an equivalent of carbon dioxide. The arrows look great. However, for the last arrow, when we break this carbon-carbon bond here, where do those electrons go? And this is important to consider. So when we break this carbon-carbon bond, do we have something that can accept that electron density? So after decarboxylation, yep, exactly right. We generate the enol form. The reason why we need this carbonyl, exactly 2 carbons away from the carboxylic acid, is because the carbonyl can stabilize this excess of electron density that we get when we break this carbon-carbon bond. So you need this electron withdrawing group, which is most often going to be a carbonyl, in order for this decarboxylation reaction to be efficient. Yep, so the student proposed mechanism looks great. Whoops, one moment. Okay, so I'm going to redraw this molecule to make it a little bit easier for us to see the key decarboxylation step. And I would encourage that when you draw out these decarboxylation mechanisms, that you draw it out to make this 6-membered transition state easy to draw. So we're going to pull off a proton, form our carbon-oxygen double bond, break our carbon-carbon bond, and we get the enol tautomer. But we're not done, right? We don't isolate this enol tautomer, no matter how convenient that would be. Instead, what's going to happen to this enol tautomer under acidic conditions? What's going to happen to this enol tautomer under acidic conditions? It's going to tautomerize to the ketone, yes. Would anyone be able to share the mechanism for that tautomerization step? Would anyone be able to show the arrow pushing mechanism for that next tautomerization step? So in this tautomerization step, we pull off a proton and then we protonate our enol at carbon. So when you tautomerize between the ketone and enol tautomer, you are transferring a proton. So this proton transfer from the enol tautomer's oxygen to the carbon to generate the keto tautomer is called tautomerization. This process of generating a tautomer via the transfer of a proton is known as a tautomerization reaction. So we're going to be able to tautomerize the enol tautomer to the keto tautomer via a proton transfer. And that in turn gives us our neutral isolable alpha substituted ketone. Does this mechanism make sense to everyone? Any questions on this mechanism before we move on? Okay, so let's try to put together each of these steps that we've learned for enolate alkylation and decarboxylation together. And let's try to predict the product of the following reaction. And then let's try to draw a mechanism for the following reaction. So let's work through this example and keep in mind we've seen each of these individual mechanisms and we've drawn out each of these mechanisms individually in previous problems. Let's try to put it together and go from start to finish. We're going to alkylate a beta ketoester in this case, and then we're going to decarboxylate the beta ketoester. So let's work through this example, and then I'd like students to share their proposed mechanism as either a photo of their written work in the chat, you can describe the mechanism in the chat or verbally, or you can annotate your proposed mechanism on the class whiteboard. And if there are any questions I can address as we work through this two-part mechanism, don't be shy to ask your questions in the chat or verbally, and I'd be happy to address them. So the first step, we treat a beta ketoester, which has an acidic alpha proton, with tert butoxide. Tert butoxide is a reasonably strong base and certainly sufficiently basic to deprotonate these acidic alpha protons, giving us our enolate. So once we have this enolate, it can react with common electrophiles, such as chloroethane, via an SN2 reaction. As a reminder, enolates prefer to react as nucleophiles centered at carbon rather than oxygen. So from here, we'll alkylate this beta ketoester. And now we're ready for the next step, which is the hydrolysis and decarboxylation. Okay, so we have this alkylated beta ketoester, and we treat it with aqueous acid, and we can even heat our reaction mixture. So these are textbook hydrolysis and decarboxylation conditions. So as in any textbook hydrolysis, we're going to hydrolyze our ester. And in order to do that, we're going to have to protonate our ester to activate the ester. And once the ester has been activated, we can now attack the ester with even weak nucleophiles, such as water. So water will attack the electrophilic ester carbonyl carbon and will generate a tetrahedral intermediate. From here, we're going to need to activate our leaving group via proton transfer and fundamentally via protonation. So we can't just lose ethoxide directly. We're under acidic conditions. So just directly losing ethoxide wouldn't work or wouldn't be the major pathway, especially because we currently have this better leaving group of water floating around. But you are on the right track. In order to get this substitution reaction to occur, we're going to need to get rid of a proton from water and protonate our alcohol. Would you be able to show those proton transfer steps? And of course, as we work through this example, If any student would like to share their alternative mechanism, or if you have any questions, don't be shy to type them in the chat, ask them verbally, or annotate on the class whiteboard as well. We have one student who's going through this mechanism and sharing their proposed mechanism, and I'm trying to narrate it to help everyone stay on the same page. But of course, there's always room for students to add to the discussion, and if there's something you agree or disagree with, don't be shy to share your thoughts. So after a proton transfer, we can now kick out our activated alcohol leaving group and generate our carboxylic acid. So in order to free up some space, what I'm going to do is I'm just going to re-annotate what we have so far, just so that way we have more space to continue on with this mechanism. But what I've seen shared so far looks great. Everyone is following along with this mechanism wonderfully, and the steps that they proposed are reasonable. So just to reiterate, we're going to deprotonate our alpha position to make this beta ketoester derived enolate. From here, this enolate will react with electrophiles such as chloroethane via textbook SN2 displacement. We've now alkylated this beta ketoester, and we're ready for the next student proposed step, which is the hydrolysis step. So
In the first step, does it matter which ketone turns into the
they're
alkoxide?
they're both resonance forms of each other.
Okay.
Though it's common to prefer forming the enol at the ketone, just mainly to convey the fact that the ketone is no longer electrophilic when you deprotonate the alpha position. Instead, this ketone is part of a nucleophilic enolate structure. And so
Okay.
we often like to show the enolate using the ketone just to remind ourselves the ketone is no longer electrophilic after deprotonation. Does that make sense?
Oh yeah, thank you.
Perfect. So as the student proposed, in order to hydrolyze this ester, we're going to protonate the ester carbonyl oxygen. From here, we can then attack the activated carbonyl carbon with even weak nucleophiles such as water. From here, we get a tetrahedral intermediate. We're then going to activate our leaving group via protonation. And we're going to free up a lone pair on one of our oxygen atoms. Okay, so now we're at the step where the student responses left off. This is where we've left off as a class. So we have this tetrahedral intermediate. So let's try to pick up from here, and I'd like us to complete this hydrolysis and decarboxylation mechanism. So after we kick out our leaving group, from here, as a cleanup step, we're going to deprotonate our carboxylic acid, carbonyl oxygen. From here, we're now ready for our key decarboxylation step. We have our carboxylic acid, 2 carbons away from a carbonyl or another electron withdrawing functionality. So from here, we can engage in this concerted decarboxylation reaction where we lose an equivalent of carbon dioxide and we generate an enol tautomer of our ketone. So now that we have the enol tautomer, we're not really going to isolate the enol tautomer in practice. Instead, this enol tautomer will tautomerize under the acidic reaction conditions to the more stable keto tautomer. So after a quick tautomerization via 2 proton transfers, we get our desired highly substituted ketone. Perfect. So the student proposed mechanism looks great. So let's clear these annotations and let's just refresh our discussion of the last few steps of this mechanism. So we lose our leaving group and we now have our protonated carboxylic acid. So from here, we're going to see a series of proton transfers. So now that we have our desired beta keto carboxylic acid, we can lose our equivalent of carbon dioxide via decarboxylation. So we'll pull off a proton, we lose carbon dioxide, and we get the enol tautomer of our ketone. From here, we're going to tautomerize this enol tautomer to the more stable keto tautomer via a series of proton transfers. That in turn gives us our desired highly substituted ketone. Does this make sense?
Is it okay to draw that tautomerization step like in 2 steps, or does it happen at the same time? Like,
You can draw it in 2 steps.
okay.
you can draw it as protonation of the alkene, deprotonation of the oxygen at the oxygen atom. That's fine.
Okay.
Any other questions on this mechanism before we move on? Okay, so let's keep going then. Another application of the malonic ester synthesis is the preparation of cycloalkane carboxylic acids. So this can be used to prepare 3, 4, and 5, even 6-membered rings via sequential alkylation of a malonic ester with a di, in this case, for example, dibromobutane, or essentially any alkyl halide that contains 2 halide leaving groups. So in this case, our malonic ester enolate attacks and displaces our alkyl halide. From there, we can generate another enolate, and it gets immediately alkylated via an intramolecular SN2 reaction. From here, once we have our desired cyclic malonic ester derivative, we can hydrolyze and decarboxylate this malonic ester to generate a carboxylic acid. Nothing unique mechanistically, but it's really important in terms of pattern recognition that you note that you can prepare these cyclic carboxylic acids and cyclic carboxylic acid derivatives using the malonic ester synthesis. Does this discussion make sense to everyone? Any questions so far? Okay. So we've already seen applications of acetoacetic esters, but let's just talk about this. This is the exact same thought process as the malonic ester synthesis, in that it can convert an alkyl halide, this time into a methyl ketone or other substituted ketone. In this case, rather than using a malonic ester, we're using acetoacetic acid ester, in this case, ethyl acetoacetate. Just like before, strong bases such as ethoxide can pull off this acidic alpha proton to make an enolate. This enolate can be alkylated. And from here, once we have our dialkylated acetoacetic ester, we can decarboxylate to get our ketone. Does everyone see the parallels between these two synthetic methods? Does this discussion make sense to everyone? Okay. So in general, we can take beta ketoesters, generate an enolate, alkylate that enolate, and then decarboxylate. This is a general synthetic scheme for any beta ketoester. This is very useful if you want to prepare substituted cyclic and acyclic ketone derivatives. So let's take a look at the following example. In this case, we're taking ethyl 2-oxocyclohexane carboxylate, which is a cyclic beta ketoester. And to really help you appreciate the benefit of going through the beta ketoester, let's look at what happens if we have a methyl group here. Okay, So we have two alpha protons that I'll call alpha and alpha prime. If we treat this compound with ethoxide, which side gets deprotonated? Which alpha proton gets removed? The proton adjacent to our ester functionality, or the proton on the other side, which is just adjacent to the ketone? Which of these two protons, alpha or alpha prime, is more acidic? The regular alpha proton, exactly right. It's a more stable enolate anion and a more stable conjugate base anion. So deprotonation exclusively occurs at the indicated alpha position. So this allows us to control the regioselectivity of our alkylation, because once we make this enolate and we treat it with an electrophile, such as, for example, benzyl bromide, we can alkylate our enolate exclusively at the shown alpha position. And then from here, once we've alkylated our enolate, we can get rid and we can remove our ester functionality via decarboxylation. So in effect, we can use a beta ketoester to control the regioselectivity for these enolate alkylation reactions. If we just started from this ketone and we treated it with LDA and then we added in our benzyl bromide, we would expect to see a mixture. So, does everyone see this key distinction between going through a beta ketoester versus going directly from the corresponding ketone? The reason why we often plan and use beta ketoesters in synthesis is because they directly control and they directly enforce regioselectivity. Only the alpha position adjacent to your ketone carbonyl and your ester carbonyl gets deprotonated. And thus only that alpha position reacts in subsequent alkylation reactions. Does this make sense? Any questions on this discussion of malonic ester and beta ketoesters in the context of synthesis? Okay, so let's try to apply what we've learned. Let's try to apply what we've learned here, and let's try to propose a synthesis of the following compound. And let's make this very straightforward and just propose a synthesis of this compound from starting materials that have 8 carbons or less. And I just want to emphasize that when we're planning a synthesis, utilizing a beta ketoester or a malonic ester can be quite useful if you want to regioselectively alkylate at only one alpha position. So we have the following ketone. We want to generate this alkylated ketone from starting materials that have 8 carbons or less. And I want only this product. I don't want a mixture. I don't want to see any other product from this reaction. I want your synthesis to be efficient and effective to make this desired product. So given what we've learned about beta ketoesters, malonic esters, and enolate alkylation reactions, how would we go about planning a synthesis to make this compound? So let's think about this for about 5 minutes, and I'd like students to share their thoughts in the chat verbally or to share their synthesis annotated directly onto the class whiteboard. So we have two positions. I'll call them 1 and 2. How do we make it so we only alkylate at position 2? How do we enforce regioselectivity? What can we do? What trick have we learned previously in this chapter? What does the class think? So we have one student drawing out. So if we want to alkylate only at position 2, we'd best use a beta ketoester to make that position more acidic. It's easier to make the enolate at that position, and thus we can selectively alkylate at that position. Yep. Yep. So we can generate the enolate from our beta ketoester. We can alkylate with a primary alkyl halide. And then once we're done, we can just clean up and lose our beta ketoester via decarboxylation. Yeah. Wonderful, wonderful. That idea is perfectly reasonable. Though in practice, as we'll learn later on, you may want to use a slightly stronger base like sodium hydride, just because sodium hydride is non-nucleophilic. Would you be able to show the conditions for decarboxylation? So as of right now, these first two conditions alkylate. That's correct. You can draw the alkylated product, but you need the second set of conditions to decarboxylate it. Yep, exactly right. H3O plus, and then you usually have to heat it. Yep, perfect. So this planned synthetic route looks perfectly reasonable. So let's reiterate, and I'd like to show you a little bit of how to think through retrosynthesis and how to annotate your retrosynthesis. So this forward route looks great. Just to show you how I'd like to organize my thoughts. If I want to prepare this compound and I want to see selective reaction at position 2, everyone noted in their shared responses, both in the chat and on the class whiteboard, that we need to go through the beta ketoester. So that way this alpha position can be selectively deprotonated and alkylated. We're then going to break this carbon-carbon bond. And that gets us back to a beta ketoester. One thing that I would like you to note, just be careful counting your carbons because the ethyl ester has too many carbons. In this case, the methyl ester, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7. Ethyl ester would also work in this case. No, the ethyl ester has 9 carbons. The methyl ester has 8. So we're in the 8 carbon limit, so we're good to go. The ethyl ester is fine from a reactivity perspective, but it just doesn't match the limitations of our problem. Okay, so now that we have our starting materials set up, we can perform our forward synthesis. So we're going to take our beta ketoester. We can use methoxide. I'll use sodium hydride just because it's strong enough. We'll see deprotonation at the alpha position almost immediately, and we don't have to worry about like retroclason and other side reactions. We'll talk about that more next chapter. So sodium hydride and then our alkyl halide. We form our enolate, we alkylate the enolate. That gives us our alkylated beta ketoester. And then from here, we just treat with H3O plus and heat. And that gives us our desired alkylated beta ketoester. Does this synthesis and does this idea of using malonic esters and beta ketoesters in synthesis make sense?
What was like the very first step?
So essentially, before we even look at breaking bonds in this compound, we first do almost like a functional group interconversion in a way, where we show that to make this compound, we're going to be going through the beta ketoester. And once we have this beta ketoester in place, it becomes easy to see that we can form this carbon-carbon bond via an alkylation reaction. So doing these kinds of annotations where you show, well, where do I get my product from? What functional groups do I need? And then using those functional groups in your synthesis is very useful because it helps you potentially notice patterns that may be hard to see if you're just looking at the final product. Does that make sense?
Yeah.
If you wanted to do it from 6 carbons or less, you'd have to use some conjugate, you have to use like conjugate addition chemistry. You can also make this as well. You can also make this using a Claisen reaction. We'll talk more about if we wanted to make this compound from lower carbon counts a little bit later on. For a typical exam, I'd give you the 8 carbon example as it really gets to the heart of this concept where we use beta ketoesters to control our regioselectivity and chemoselectivity. Yeah, but there are a few ways that I could think of. I would probably go from, if you wanted to do a 6 carbon route or a 5 carbon route, you can probably go from like cyclopentanone and do like a conjugate addition followed by alkylation. That's one way to do it for those who are curious. But there are many ways that you can come up with that would work. You can also make this from an epoxide opening. You can do something like this. So there really are a range of tools at your disposal. Did that answer your question? But I'm very pleased to see the way the class went about solving this problem. Okay, so let's do one more. Let's do one more just to make sure we're comfortable with this. How would we propose a synthesis of the following compound from molecules containing 4 carbon atoms or less? And this time the 4 carbon atom rule is a hard limitation. So make sure your starting materials have 4 carbons or less. So as we work through this example, I'd love for students to share their proposed synthetic route as a photo in the chat, or you can explain what intermediates and species that you'd go through, or you can annotate your proposed synthetic route on the class whiteboard. And if there are any questions that I can address as we work through this example, don't be shy to ask your questions in the chat or verbally. So how would we go about preparing this compound from materials that have 4 carbons or less? So what do we think? Does anyone have any initial ideas? So you can think of this almost like we're going to have to alkylate our alpha position. And it's pretty hard to alkylate one alpha position preferentially, especially if it's the more substituted position. So what can we do? What method do we have at our disposal if we want to selectively alkylate one of our alpha positions? Would anyone like to share their thoughts for this synthesis? Would anyone like to draw out what bonds they're thinking of breaking to get to simpler starting materials? Or would anyone like to draw the starting materials that they're using in their synthesis? Again, I would highly encourage you to use retrosynthesis and to think backwards from our starting material and to think backwards from our product to get to manageable starting materials. So, does anyone have an initial set of thoughts that they'd like to share? Yeah, considering that we have this ketone functionality and considering we want to selectively alkylate this alpha position, it would be reasonable to trace this back to an acetoacetic acid-like compound. Okay, So from here, what do we do? How would we prepare this substituted acetoacetic acid derivative? What bonds can we break now that we have this functional group retrosynthetically installed? So we traced back this ketone to the corresponding acetoacetic ester. From here now, we see one of our alpha positions is highly substituted. So how would we go about installing these alkyl groups? Do we have a method to install these alkyl groups? We can go through the alkyl halide, sure. Would you like to draw that out? Would you be able to draw out the starting materials that you'd use for that then? Or at least show what carbon-carbon bonds we're breaking?
Would we do it twice?
Yep. Remember,
Okay.
for malonic esters and for acetoacetic acid-derived esters, we can sequentially alkylate these beta ketoester compounds. So we can trace this back to the methyl ester, and this has 5 carbons currently. So how do we get to 4 carbons? Can we trace this back to an even simpler starting material? Is there an even simpler starting material that we can use? What's one way for us to get rid of a carbon here? Is there an easy way for us to get rid of a carbon? Yeah, we can just lob off this methyl group and trace this back to the carboxylic acid. Or, as we'll see next chapter, we can trace this back to just the normal ester. We'll talk about that reaction next lecture block. Wonderful. So we have our retrosynthesis that we've generated as a class. Now, would anyone like to try to take this retrosynthesis and write a forward synthesis with all of the conditions and reagents that we'd need? Would anyone like to try to propose a forward synthesis? So would anyone like to fill in the conditions to go from our reactant to the product? So if we start from this carboxylic acid, and we want to go to this methyl ester, what conditions do we use? What conditions would we use? Let's work on this together. So we had our retrosynthesis. Everyone shared their thoughts for the retrosynthesis. Let's talk about our forward synthesis. How would we go from the carboxylic acid to this methyl ester? That's our first step. What would we need to do? Yeah, you can do a Fischer esterification with methanol and hydrochloric acid. Yeah. Okay, perfect. So we get our desired methyl ester. Okay, so what about the alkylation conditions? So we've tried to break these bonds off and we trace it back to these alkyl halides. So how do we alkylate a beta ketoester? What conditions would we need to use? How do we alkylate a beta ketoester? What combination of reagents would we need for this enolate alkylation reaction? Yep, so we need an alkyl halide, sure. And how do we actually make our enolate? How do we actually deprotonate this alpha position? Yeah, you can use tert butoxide. That's more than suitable. And if we're doing a sequential alkylation, we add our base and then we add our alkyl halide. The order isn't super important, but I would probably alkylate with this isopropyl bromide first before adding ethyl bromide, just because isopropyl bromide's more hindered. Okay, so we've sequentially alkylated our alpha position. Now what? How do we close out this synthesis? How do we decarboxylate? What conditions do we use? What conditions would we need for decarboxylation if we want to get rid of this ester? We need not just acidic conditions, but aqueous acidic conditions. If we can't hydrolyze the ester, then nothing would happen. Perfect. So we've planned out our synthesis from start to finish for this desired highly substituted ketone. Does this synthetic logic and does this synthetic scheme make sense to everyone? Any questions on this problem? If we don't have any other questions, then we'll archive our recording